Hello. So now we are going to speak about the second part of the nature of sound. So in this part, we're going to speak about sound waves and how they are generated. And then also how to calculate. We'll do some basic calculation. There will not be too much, obviously, because computers can do a lot for us nowadays. So let's begin. A sound wave is a disturbance in the pressure of air, because we use air as a medium. So that pressure moves through a medium, and as I explained, a medium is, the environment. Basically, it could be water, like whales, dolphins communicate underwater. You can make sounds underwater as well. So air is a medium, water is a medium, a solid like wires that we use for telephones and TVs and so on. These are all media. Media is the plural of medium. So, and then a wave front. It is the outer limits beyond which the wave can't travel anymore. Like if you stand somewhere and call someone's name. Let's say the person is 20 feet away. That person will hear you. But if there's someone who is, let's say, a half a mile away, that person is not going to be able to hear you. So it depends on how loud your voice is and how far it projects. At the point where it cannot be heard anymore, that becomes the wave front. There are calculations that we do not need to go to. There's an equation that says, as you move away, as the sound moves away from the source, gradually it diminishes in energy by a factor of 1 divided by the distance. So again, we do not need to calculate in this area, but the idea is, as you make a sound, I make a sound, it is like I am shooting an arrow. Once I let go, all the energy I gave to the arrow is already given. I will not add any more to that energy. How do I add energy to an arrow? It depends on how far I pull the string away, how far I pull. Obviously, the farther I pull, the greater the elastic force that will try to pull me back or pull the arrow back to that rest. And if I would like the arrow to travel just a shorter distance, I'm just going to pull a little bit. So in any case, once I let go of the arrow, that I loaded it with energy, and then I let go, it takes that energy and it travels with it. I cannot add any more to it while the arrow is traveling in space. So as a result, that energy I put, it gradually diminishes step by step by step by step until the arrow has no more energy and it will fall down. The same applies to a sound wave. When you make the sound, air molecules are going to be displaced. They will be pushed away from you, and they will travel and travel until, as they travel, they diminish in energy. And this is why, if you are closer to me, you are going to hear the sound as louder. And the next person, like 2 feet behind you, will hear my voice as softer. And then someone who's 4 feet away, and gradually, until you reach one person at the very end of the auditorium who cannot hear the sound at all. This is called damping. Damping is loss of energy due to friction. We'll speak about it again frequently. Simple harmonic motion is a motion that is produced in a predictable way. So it is back and forth, like the movement of a pendulum. So here's the rest, and I want to make a movement. I go, say, like 3 inches in this direction, go back to rest, and 3 inches in that direction, just like a pendulum or a swing. And if that, movement here from rest to my left side is 3 inches, then when I go back to rest, the movement on my right side will be also 3 inches. So they are equal on both. So that makes one cycle of vibration or one cycle of oscillation. So harmonic or harmony basically, it's a condition where you can predict things. You see them happening exactly. There are no surprises. So, there's less stress and things are just predictable and great. So simple harmonic motion, to think about it, think about a pendulum, think about a swing, anything that just repeats itself in a rhythmic way, back and forth. Hooke's law that we spoke about yesterday is the only condition that is needed to produce a harmonic motion. What did Hooke's law say? I'd like you to answer that question, maybe write it down. So you don't have to memorize it, but just know the concept is this: that elastic force that brings objects back to their original condition after being distorted or deformed or displaced, that elastic force increases gradually as you take the thing away from its rest position. The second piece of that is that the elastic force pulls the object back again in the opposite direction. So I'm taking it away from rest and it is trying to bring it back to rest. No, go back to rest. So if I pull 1 inch, elastic force will increase by 1 factor. The farther I go, the greater the elastic force that is going to pull me back to the original position or placement of the object. So in effect, that is going to produce 2 equal distances from like say, here's the rest area, and you take that pendulum or the swing, pull it 3 inches this way. Once you let go, it's gonna go back to rest, and it's gonna swing past rest by 3 inches exactly the same way. So that distance here on this side and on that side, that makes one single oscillation or one single wave. So again, the single most important requirement for producing simple harmonic motion is that the elastic force of the moving object is proportional to the degree of displacement of the object. Proportional means if you pull 1 inch, then there will be an increase by 1 unit of force, for example. If you pull 2 inches, it will be an increase in elasticity by 2 factors. And as you keep going gradually, you can predict it, you can calculate it. So also the other piece, as I mentioned, is that the elastic force is going to work in the opposite direction of your movement or of the movement of the object that is moving. A cycle is one back and forth movement of a molecule. When you say a molecule, air molecules, combine in different ways and they float around in the air. So, one way to demonstrate the movement is to simply use a swing or a pendulum. So you have say for example, this is the rest. This is where the swing is hanging at rest. And I'm going to displace it away from rest. Let's say by 3 feet, and then I let go. So this is one part, and then it's gonna go back to rest and swing back on the opposite side by 3 feet, the same way, and then it's gonna come back to rest again. So that makes one complete cycle, just like this. Instead of that in the sound, to make it simple for us to see, we depict it like that. Now this is 1/2 of the cycle, this is 1/2 of the cycle. So, and then, but this is just one cycle. The idea is you start it at one location, from one location, from rest, go away, come back to rest. This is 1/2 of the cycle. Swing on the opposite side, come back to rest, then that's the second half. And it is depicted like one peak, and then you dip down into a trough, go back to rest. So it will be this 1/2 and another half. The period here, it obviously, see, cycle refers to a distance, going back, going forth. Period refers to the time. And this is why, the period, the symbol for period is T, means time, the time that it takes to complete one complete cycle. So here's again the swing, or the pendulum. It is at rest. I displace, and then let go. It goes to rest, and then goes on the opposite side, comes back to rest. That is one complete cycle. How long did it take to complete that cycle? That is the period. Frequency now, all of us, kind of use this concept on a daily basis without saying, oh, look at, we're studying sound. Frequency means how frequently something happens. For example, think about yourself. How frequently do you go to the movies? So one of you will say, well, I go once, and then what's the other piece? So in frequency, there are two pieces, a number of times and a time. So you say, oh, I go once. Someone will say once a week. Once a week. And then someone will say, well, I go once a month. So I said, well, tell me about the frequency, in a year, for example, or in a year. How many times do you go in 1 year? All the times that you go. How frequently do you go? So, well, 12 times per year. Or if you go, 4 times a month, then you calculate 4 times 12 months. That will give you the frequency, the total number of times that something happens. How frequently do we have rain? So, well, we have rain, if you have 1 unit of 1 month, so we have rain about, 5 times a month, or maybe 10 times a month. The entire month, this is all the rain that you have. So frequency is the number of cycles that can be made, that are made in a single second. Remember, in sound, in order for any sound to be made, it has to occur within a single second. It has to be fast enough. It has to occur fast enough so it can make a certain number of vibrations in 1 second. If, for human beings, if something vibrates 20 times, 20 cycles, 20 times per second, then, and you have perfect hearing, that 20 times per second is going to make a sound that you can hear. But it will be, of course, the faintest sound that you can hear. There's a concept that I'm going to explain again, go back to the frequency. Let's say someone says, yeah, I go to the movies 4 times a year. Someone says, no, I go to the movies 12 times a year. So when we look at the person who goes 4 times a year, we say that is low frequency. It means it doesn't happen, many times, per year. And the person that goes 12 times a year compared to that will be, high frequency. The event is happening many, many times more, high frequency. So we always, when we speak about frequency, describe it either as high or as low. So high means it happens, the vibrations happen many, 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 many times, at a fast rate. And low means, the number of vibrations per second is less. So again, frequency is the number of cycles of vibration that are made in a single second. And instead of saying that, for example, or let's say the hummingbird. Now we have hummingbirds coming in our neighborhoods, and they will be there probably even more in 2 weeks or so. These little, very, very tiny hummingbirds. Listen, watch their wings and listen to them. Or if you don't have some nice flowers in your backyard, go online and listen to a hummingbird, YouTube hummingbird, and listen to the sound that it makes. It goes like this. So that is try to guess and answer the question tomorrow. How many times does a hummingbird flap its wings to make that sound that you can hear? And you tell me, this sound, is it a high frequency sound or is it a low frequency sound? So instead of saying, let's say a given, something happens, let's say my vocal folds vibrate 100 times per second to make the sound I'm making. So instead of saying my frequency, or the frequency of the vibration of my vocal folds is 100 times per second, that's a lot of, many words. So instead of that, we simply say 100 Hertz. Hertz, with a capital H, is the name of the person, of the scientist, I think German or Swiss, who made these calculations and figured them out. So instead of saying cycles per second, we say Hertz. 100 Hertz is 100 times or 100 cycles in 1 single second. And again, remember, we never, ever, ever measure sound beyond 1 second. If it is not happening in a single second, there is no way that we can hear it. So now here is a graph, and this is called a waveform. Waveform. And the waveform is a simple graph that depicts the wave. So the line, horizontal line, shows you the time and the distance of the wave. The vertical line shows you how much energy is in the wave. Think about it as, if this rest is where a guitar string would rest. And then you pull the guitar string away from rest. You displace it. And you pull it as far as this point, A. That means, or similar to a bow, a string, when you pull it, the farthest point that you pull it at is the maximum point of displacement. Now that maximum point of displacement is going to determine the amount of energy that you are putting into it. Obviously, the farther away you pull it back, the greater the amount of force, the greater the elastic force that's gonna pull it back to rest. So that amount of energy is going to determine the loudness of the wave. So loudness depends on the energy that you put into producing the wave. So always on the left side, we have the maximum point of displacement, which means the amplitude is, which means the amount of energy that you have, or the loudness of the sound. So we commonly make it here decibel, vertical, decibel, like 0, there's no sound, and then 1 decibel, 2, 3, 4, and so on. And also below on the other side, you also have minus, -1, -2, -3. It doesn't mean there is no sound. There is, but we'll explain it later. So here, the maximum point here, maximum point of displacement, we call it the amplitude, we call it the maximum point of displacement, and we measure that maximum point of displacement in decibel units. Just to make you understand, decibel means it's a unit that measures loudness or energy of a wave. It is named after Alexander Graham Bell, who was, you know, in the old days, in the 1800s, used to be the speech language pathologist of that day. He's the one who invented the telephone by working on sounds and how people hear sounds and so on. So he made these measurements, the decibel scale, and then so you see DC means 1/1000 or 1/100, and then Bell with a capital B, it stands for Alexander Graham Bell. So the peak of the wave here is, it stands for compression, and then you go to below rest, then you have rarefaction. Compression is produced by a direct force, a direct amount of energy that you put, like you pull the guitar string. Now you have loaded it with energy, and then you let go. That force is gonna let it go to rest, but then you get a little bit more. It is inertia is going to pull it, make the string travel into the opposite side, and it will give you energy on the opposite side, but that energy is additional. It is caused by inertia. So this compression and this rarefaction together, they make the wave. Compression makes half of the wave. It ends here at rest, and then rarefaction makes the other half, which also ends again at rest. If you want to now measure the length of the wave, you can measure it here on this line, how long it is in feet, or in yards, or in meters, whatever it is. You can also measure it in time and see how long it takes, you know, for this wave to be made. So again, the horizontal line, there will be a question in the exam asking you about the waveform. What kind of information does it display? So the horizontal line displays the length of the wave. The horizontal line also displays the time it takes for each cycle, or it displays the period of the wave, and the vertical line displays the point of displacement, which is also the amplitude, and it is usually measured, the units are measured in decibel. So here you could see now we're using decibels. Here 0 means there's no sound at all, and then the peaks. Let's take this wave here. It goes up when the peak reaches 10 decibel, and then as the wave goes, as the air molecules go down to rest, they swing to the opposite side because of inertia and go back to rest. So that is 1Z. 1Z makes one complete wave, and then the other wave begins also here, and it makes 1Z. So a wave doesn't have to start exactly here, but it is 2 points that are across from each other are gonna make a wave. So answer this question. Which wave here is louder and why? So here, the maximum point of displacement is 10, and on the other opposite side is, it gives you minus 10. And this maximum point of displacement is 30 decibel, and on the opposite is also 30 decibel. So that is a harmonic wave, that is a pure tone wave, and obviously the second wave is louder than the first wave. So now, pitch, let's go back to frequency. Frequency, we said, is the number of vibrations, the number of cycles in a single second. How we hear that number of vibrations, when something vibrates, it's going to depend on our own ears, our own brains, and how we get the sound, how we perceive the sound. For example, someone is going to listen to me and say, oh, his voice is loud. Or someone else sitting a couple of feet away is going to say, oh, I can't even hear him. Someone is going to listen, oh, I think his vocal folds by pitch is very low. And someone will say, well, I think it's okay. It is not very low. So the idea is this. On frequency, there is no disagreement at all, because a machine measures the number of vibrations per second. If something vibrates 500 times per second, there is no guessing about it. It is the absolute number you measure, and there is no disagreement. If you have 10 people listening to that 500 vibrations, and you say, can you predict, can you guess how many, vibrations there are? No one is going to get it right. So someone's going to say, well, I think this is a low frequency sound. Someone says, oh, it's a mid-range. Someone says, this is a high frequency. The idea is pitch is our guesstimate of frequency based on our own ears, based on our own brains. All of us tend to differ in terms of pitch, but we just grossly say, yeah, males have a low pitch, generally. Females have a high pitch, generally. Young children have a high pitch, and as they grow older, they have, their pitch becomes lower and lower. So pitch and frequency refer basically to the same thing. However, frequency is the absolute number. There's no guessing about it. Pitch is our guesstimate of the frequency. Okay, so it differs. Pitch is the subjective. Subjective means, my feelings get into it. Objective, it means no, you are out of it, and no matter what happens, your feelings do not get mixed up. So pitch is the correlate, subjective correlate or subjective perception of frequency on a musical scale. So in other words, the higher the pitch, the higher the frequency, or the higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch, because they are basically referring to the same concept. Now, which sound would be perceived as a higher frequency? 100 hertz or 1000 hertz? As I explained earlier, when someone says, I go to the movies 4 times a year, that will be low frequency. The one that says I go 12 times a year, that will be higher frequency. So which one is higher frequency here, 100 or 1000? Great. I know you got it. So frequency and period are related in a reciprocal way. In other words, if you figure out one, you are able to figure out the other one. So period and to figure out either one, you just have 1 divided by, frequency or period. Like if you want to figure out period, say period equals, or T equals 1 divided by frequency. Say my vocal folds are, vibrate 100 times per second. You want to figure out how long does it take to make a single vibration. So you say, okay, that's easy. A single vibration is 1 cycle, and I want to figure out the period for that cycle. Frequency is the 100, and I'm looking for that period, which is T. So I say T equals 1 divided by 100, and then equals, and then you get the number that tells you how long it takes to make a single vibration, if out of these 100 vibrations, because all of them fit within 1 second. Let's say I don't know how many times my vocal folds vibrate per second, and then all I know is I have how long it takes for 1 single vibration that my vocal folds make. So you say, okay, frequency, the total number of vibrations, equals 1 divided by, and say for example 0.001, and you do all these calculations on your calculator, and you will be allowed to use the calculator in the exam. So, and then the number you get is going to be the frequency, the total number of vibrations per second. We are going to do many of these exercises in the classroom. So I hope that things are clear as we go. I feel everything is very crystal clear at this point, but I would like you to keep writing questions and make questions for your colleagues, and to develop an exam, and also at the same time have a list of questions that you can ask in class, because I would like to make sure that you absolutely understand the material. So, but I wanted to clarify what that 1 stands for. 1 is the unit of time that the whole thing has to occur in. It has to happen in. 1 is the 1 second. I told you that frequency is the number of this and this that happens in a single second. So 1 stands for 1 second. And if you want to figure out period, how many, what is the length of 1 vibration in 1 set, then you say, well, divide 1 second by the total number of vibrations. Like I have $1 and I have 10 people. So I divide $1 divided by 10. I find out how many pennies each one of these 10 people will get. Or I have 10 people and each one has 10 cents. And I would like to figure out how much in all do they have. So well, 10 cents, times the number of people I have, that's going to give me my frequency. So because periods are all parts of the frequency, you can, if you know frequency, you can predict period, or if you know period, you can predict frequency. So as the number of cycles per second increases, the time it takes to complete a single cycle is going to decrease. The opposite way is, because they are reciprocal, the opposite situation is also true. As the frequency goes down, period goes up. Let's explain. Actually, I had an image later, but I'm going to show it later. let's say that two people that, I have a student and myself. We stand next to the board in the classroom, right next to the wall where the screen is. And we go have a race to go to the opposite side of the room, to the opposite wall of the room. And you guys time us, give us 1 single minute. Of course, sound is in one second only, but I mean, we can't just, move back and forth in 1 second, unless we... So let's pretend. So 1 minute, you give it to both of us. And you say, you go as fast as, you take trips from this wall to that wall. Let's say the student goes very, very fast. Twice as fast as I am. From the wall to the other wall. Makes maybe, actually, let's do it this way. So the student goes from one wall to half of the room. Exactly half of the room. Maybe 10 feet. And I go from one wall to the opposite wall 20 feet. So I cover twice the distance. And you give us the same time. You see here, 1 minute and set, go. Who do you think is going to make more rounds per minute? The student who travels 10 feet and goes back and forth 10 feet, or myself who goes from wall to wall 20 feet at a time? Obviously, the student will make more cycles per minute than I do. However, these cycles are 50% less than my cycles. And I go, my cycles are long. The longer they are, the more time it takes to make them. So if the student, now this is my question to you, if the student who travels 10 feet per cycle covers 10 cycles, how many cycles will I make in the same minute? I hope you get the answer correctly. I gave you even numbers. Okay, I think you have gotten it. So the idea again is the longer the cycles are, the smaller the total number that can happen in a single second. And the smaller the cycles are, the greater the frequency, the greater the total number that can happen in 1 single second. So I hope this makes the concept clear. I don't want to make, over explain things and then make them not clear. Now here's one exercise. We are going to get several of these in the exam in the form of different forms, but some of them could be true, false, some of them could be multiple choice, especially multiple choice, and sometimes you are given one short answer question that you need to calculate. But in any case, to answer multiple choice questions accurately, the answer will be in one of 4 or 5. And then you use a calculator to figure out, and then the one result that you get that matches one of the options you have will be the correct answer. So we would like to determine the period. If a pendulum oscillates at a rate of 10 times 10 cycles per second, or let's say scientifically now, if the frequency of a pendulum is 10 Hertz, what is the period? How long will it take for one of these 10 vibrations to occur? What is the length of time it takes one single vibration? So your magic equation will be 1 divided by 1, you're looking for period, which is t, equals 1 second divided by 10 equals, and you run it into your calculator, and this is what you get. But remember, when in here, what you do, you say equals 0.0 or no 0.1, and then you say SE second, because they are measuring time. What is exercise 2? What is the period of 1000 Hertz tone? So let's do it. Maybe that will show here. Say 1 divided by 1000 equals, so 0.001. That is 100 milliseconds. And then the unit is say SEC. That is the unit of time, SEC. So remember again, keep the equation in mind. In either case, if you want to calculate period, you say 1 divided by frequency, because you are given frequency. If you want to, if you are given frequency and you want to figure out period, say 1 over frequency, you get period. If you want to figure out period, you say, frequency, you say 1 divided by period. Now, exercise 3, a given vocal fold completes 1 cycle of vibration in 300 milliseconds. How many vibrations per second will this vocal fold produce in 1 single second? So now you get the number, the time it takes for a single cycle. It's like saying we have 100 people and each one of them gets 1 penny. What is the frequency? How much money do they have in all? So, well, and then you do your calculation, as we did it now. So again, we say 1 divided by 0.003 equals 333, 0.33. So when you write these numbers, you can go 2 after the point, you get 2 numbers, and you don't have to round, just put them as they are. So generally, that tells us that this vocal fold vibrates 333 times per second. I can tell this is a child's voice, particularly a child who is around 7 or 8 years of age. And you will learn how to guesstimate these later as we discuss the values of people's vibration rates. What is the frequency of a wave with a period of 0.004? Please do not trust your mathematical abilities too much. Always use a calculator, because these fractions could be very, very misleading. So what you do is you simply just go here. What am I looking for? I am given the amount of time for a single vibration. I'm looking for the total number for the frequency. So my equation is 1 divided by 0.004. And guess what? I get 250 vibrations per second. And I say, definitely, this is the voice of an adult, college age female, like between 18 and 22, 25. Waveform, as I explained earlier, is the graph that shows us the shape of the wave and the rate of vibration per second. It shows us on the horizontal line, our axis. It shows the period, the length of time it takes to make the cycle, and it tells us the frequency, because if you have one single cycle, you can calculate the number of cycles that can occur because you only have a single second. So that is always given, a single second. If you know one single cycle, you can figure out how many can occur in a second. So the horizontal line gives you the period, the time it takes to complete the wave, and it tells you how many waves can occur in a single second. And it also gives you the wavelength, the physical length of the wave, how many feet or how many centimeters the wave is, in addition to the vertical line that gives you the point of displacement or the amplitude, or as we know, the amplitude is measured in decibels, loudness. Wavelength is the distance, physically the distance that a wave travels in a single, one complete cycle of vibration. Because my sound waves are made out of the same cycles, they just repeat themselves. So a distance traveled by a single complete cycle of vibration, that is called a wavelength, and the symbol for it is lambda, which is the Greek symbol for that is used for wavelength. It is measured in meters, it is measured in centimeters or feet, and again the symbol is lambda. And we'll do more exercises on this to calculate. But first, I'm going to show you how to identify the length of a wave. If you take like you have two waves, two identical waves. So here's one beginning at rest, going up to one compression, back to rest, going down to one rarefaction, back to rest. That Z, that is one complete cycle. The next cycle is going to start also here, compression, and then rarefaction. So if you have two complete cycles, you will be able to identify the length easily by having 2 points on equal areas, on exactly across from each other on these two waves. So if you go to the very top of the compression here of this wave, first wave, and you go to the top of the compression of the second wave, and then you go bring a measure from here, go down, measure, all of this way here, that is going to give you a single wave. That's the length of a single wave. Okay. If you go to this point here, for example, on this wave, and exactly the same point on the other side, on the other wave, and draw a line, and then you take that string and trace this, and trace this up, you get that string is going to make the length of the wave. And this length of the wave is going to equal the other one. So any 2 points are going to give. So if you get this string and cut it from here to here and put it there, and then get that string from here to here and put them next to each other, they will be perfectly the same length. You can make the 2 lines, one here and one here, and cut the string and measure it, and then you're going to get exactly. So a wavelength is the distance from any point in one cycle to the corresponding point in the next cycle. As we look at the waves now, how they are oriented, the peak always stands for compression. There's more air molecules compressed together. And then the trough means always stands for rarefaction, means less air molecules because of the the energy. The compression means the molecules, instead of being spread about, they are compressed in one area, and then the other area is left without having as many. So always alternating compression, rarefaction, you will never have it any other way. Always repeated in the same pattern in any given wave. So the length of the wave goes also with frequency, goes also with period. Go back to the example I gave you in the class. I am racing with one of the students, one of you, and the student goes 10 feet and I travel 20 feet. So the length of that trip for the student, the physical distance, 10 feet, is the length of the wave. Okay? And then you say, how long does it take how long does it take the student to travel that 10 feet distance? That is the period. And how many trips in all does the student make in one single minute? That will be the frequency, except that in sound we use seconds. In my case, the length of the wave is 20 feet. So that is a greater wavelength. However, what is the number of cycles like? Do I have less or more than the student? So the idea is, the greater the wavelength, the greater the period. In other words, the greater the distance that the wave covers, the more time that you need in order to do the traveling. And the greater the frequency, then what happens to the wavelength? The greater the number of vibrations in 1 second, the smaller the wavelength. So that is also a reciprocal relationship, because when I cover a trip that is 20 feet back and forth, I just cannot make as many trips in that single minute as the student does. So again, the relationship between period and frequency is reciprocal. One increases, one decreases. The same, the relationship between wavelength and frequency is also reciprocal, meaning that if one goes up, the other must go down. So think about it this way. Here are two wheels, and you can ride this bicycle for 1 single minute, and then say, how long will each one, how many rounds will each one of these cycles of these wheels make in that single minute? So what is your prediction? Will the bigger wheel make more rounds, or the smaller wheel in that single minute? So you obviously got it right. The smaller wheel is going to make more rounds in a single minute, more rounds. Each round is going to take a shorter amount of time. The period will be, smaller. And the length of the wave, which is the circumference of that wheel, if you get a string and put it around the wheel, and then take that string and spread it, then that will be the length of that wave, of that cycle. And obviously the bigger wheel is going to have a huge wave length compared to the smaller one. So as a result, you are going to have the bigger wheel is going to cover a greater distance. It will make less cycles per minute than the smaller wheel. So again, the more cycles you have in a single minute. Again, we are speaking about a wheel. We are not speaking about sounds. So the minute for the wheel, but for sounds we say second. So the greater the number of cycles that are made, the smaller each wavelength, the smaller the period will be, and the smaller the number of cycles we have, or the greater the wavelength that we have, the greater the amount of time it takes, and the less that we can fit in 1 minute. And this is again an explanation of how wavelength and frequency are reciprocally related. Waveform. We said the waveform is the graph that depicts the wave in terms of one peak, one trough, and the horizontal line and the vertical line. So high frequency sounds that have more vibrations per second, occupy less space. That means if I stand, like say the same, I stand in front of the class, and let's say the class has 100 rows of people, and I stand, and next to me is a child who is 2 years old, and I say ah, and the 2-year-old says ah at the same loudness. Obviously, the 2-year-old's vocal fold vibration is going to be much higher than mine. So the wavelength for that child is going to be approximately maybe 2.5 feet or 3 feet. So it is going to reach, let's say we're standing in front of the class, it might reach 1 row, 2, 3 rows, for example. And then it will be a point where, people cannot hear it beyond that. My wave is going to be about 3 times as long, 9.5 feet. It's going to travel 9.5 feet. So it is going to cover a greater distance, even though we are standing, we're standing next to each other, and then each of us is going to make a wave. So one is going to travel just 2.5 feet, and it will, there will be no more travel here. The distance is small, and then my wave is going to be long, and it will cover a greater distance. Oh, so that means like less space. More space for mine. So low frequency sounds occupy more space per cycle, and they have a longer wavelength. So they stay in air for a longer time. Now the question is, which frequency travels farther? High frequency or low frequency? Low frequency has longer wavelengths. It covers a greater distance. It travels farther. I'm not saying faster. I'll tell you why at some point. So now, calculating the length of a wave. Now you are freaking out. Oh my God, I'm doing math. Lambda equals velocity divided by frequency. It is much simpler than you think. So the length of the wave equals velocity, the speed of the wave, divided by the frequency, by the number of vibrations that happen per second. You will always be given velocity. Velocity is the speed of sound. It's a sound constant. And that speed of sound now, for anything, any sound at all, is 331 meters per second at freezing temperature and at sea level. The pressure, sea level, and freezing temperature. You will find it, some other sources will say 330 meters, but that is fine. So 331 meters per second at sea level at freezing temperature, because we understand that if you go higher or lower, the pressure is going to change and so on. And remember now, we are not speaking about living things. We are speaking about absolute values, because later we are going to say, oh, the speed of sound is different, you know, in our bodies because we are 98 degrees or 97.6 degrees. But for now, this is the speed of sound for anything at all, living, non-living. So 331 meters per second at sea level at freezing temperature, 32 Fahrenheit or 0 centigrade. So I simply want to figure out, if I am standing here, how far does my sound wave, a single sound wave, travel? You know, how long is the length of that wave? A woman's voice has a fundamental frequency of 225 hertz. What is her lambda? The vibration of the vocal fold, physical vibration. The vocal folds are muscles that are going to go, you know, go like this, vibrating like this, back and forth. And they make 200, excuse me, for females, they make twice as many vibrations as males. And again, this is something that we are going to speak a lot about. So the actual movement of the vocal folds back and forth, we call that the fundamental frequency. Fundamental, we say F0. So the fundamental frequency of a woman's voice is, this particular woman is 225 hertz. And we want to figure out how long is a single wave out of these 225 waves that she makes. So using the equation, we say lambda equals, lambda is the wavelength, equals the sound constant 331 divided by, and then 225. But that is not going to make any sense, because we are looking at very tiny structures, 225 vibrations per second. And then I am using 331 meters. Remember, if you are speaking about meters, you have to speak about kilometers or, you know, bigger measurements. And here, it is not, it's going to give you a number that makes absolutely no sense. So let's just see, and then I'm going to give you the right calculations. So here you got 1.47. In a way, it just is, what is that? In this case, 1 meter, the length of the wave is 1 meter, 0.47. Because we are not used to the meters. So we can also think, you know, in a more practical way to make it more concrete for us. Let's say feet. So for feet, we say 1100 feet per second is the same as 331 meters per second. So 1100 feet divided by 225 is going to give you that in feet. So you say, oh, the wavelength for that woman's voice is 4.88, which is a little bit less than 5 feet. So the sound wave is going to go 5 feet away from her. Actually, it's going to go 2.5 and go back 2.5. So we'll explain that in class. So, but here, so the sound is, the wavelength here is 4.88. So what you do again is to put the sound constant, if you want to get it in meters, 331 divided by the frequency, 225, is gonna give you 1.47, 1 meter, 0.47, almost like 1.5 yards. That will be the length of that wave for that particular woman, because all of us have, different pitches or different frequency measures. So a man's voice is 115 hertz. I mean, the fundamental frequency for an adult male's voice is 115 hertz. What is lambda? What is the wavelength? So exactly, use the same equation, and you say, if you want the meters, 331 divided by 115 equals, and then you get 2.87, which is a little less than 3 meters. But again, it might be tough to make sense out of this. If you use feet, say 1100 feet divided by 115 gets it to you in feet, 9.56 feet. So that would be the adult male's, the wavelength of a single wave that this adult male's voice is going to cover. So again, you're going to have several examples of these, several questions like this in the exam, and I hope you are ready. It will be good to study that with a group, and we'll discuss it in class, and we'll do more exercises. So tones that are produced by simple harmonic motion are called pure tones. Pure tones. They just are basic, and they have a predictable pattern. They have one peak, one trough, and that is all. And that repeats itself in the very same way all throughout the wave. So they include a single type of wave, and that wave is it has a predictable pattern. It happens exactly like if it has a compression, you say, oh, it's going to have a rarefaction. And then the length of, the peak, maximum point of amplitude on this side is going to be exactly equal to the maximum point of displacement on the opposite side. So everything repeats itself exactly in the same way. I will bring some tuning forks to the class to show you what a tuning fork is, but I have it here in the next couple of slides. So a periodic tone that is, is a tone that is made by simple harmonic motion. We also call this a periodic tone. We call it pure tone. And you will be doing pure tone audiometry. You will do some hearing testing in the clinic where you test someone's hearing using an audiometer. And when you test pure tones, they are called, pure tone testing results. And if there's no pattern, then that will be an aperiodic tone. So you see, aperiodic means the opposite of periodic. So periodic compared to aperiodic tones, I'd like you to know how to compare between these two and to be able to answer a question in the exam about them. Periodic means when added, they always give you a bigger or a louder pure tone. Periodic means, let's say you have two people and both of them have exactly an identical voice, exactly the same number of vibrations per second, the same loudness, and they stand together and one person sings or says ah, and then the other person sings ah. Each one has a both of them, let's say, sing at 10 decibel. Then you have both of them stand together and in perfect harmony, you have them start saying ah exactly at the same time. What will you get? So both of them say ah. If the sounds are identical, you are going to have a single sound. If someone is not looking at these two people, that person will think that they are a single person saying ah. So again, you have two sound waves that are pure tone, that are identical, and that they are played at the same loudness level. Exactly, they match, they blend together into a single tone. The only difference is that new tone is going to be twice as loud as, you know, the single one of them. So, in aperiodic, when you combine the waves, they always produce an aperiodic tone, which is random. There's no pattern of vibration that you can predict. Periodic, the pattern of vibration always repeats itself. This is what the idea is. If there's a pattern, it means it repeats itself. It always makes harmonics. Harmonics is a concept that we will discuss in class, and there will be a lot of demonstrations to explain how harmonics are made. So harmonics are signals that are integral multiples of the lowest or of the fundamental frequency. In other words, if you get a slow speed camera and you get a guitar string or a string and you pluck it one time, let go. The first time, the whole string is gonna go down to rest, below rest, and then that will be one gigantic wave. When you let go of it, I mean, after that wave, as it goes back again to rest, and then bounces on the other side, you notice that it is going to have two pieces. One is going to be rising up as a peak on one side. The other one is going to be on the up, below the line as a trough on the other side. So that string splits, and then half of it will vibrate at its own rate. Each half will vibrate. So that will become a harmonic. And then they continue to vibrate. That half is going to go rest, past rest, come back again, and it will split into two more smaller pieces. So the whole string will be 4 little pieces vibrating. And it repeats again. It will make 5 pieces, 6 pieces, 7. So each segment of the string then is every time is going to split into a half, and you go from one single string to, let's say 4 feet string to 2 feet, 2 feet. Each segment is going to vibrate it's going to make its own wave. And then the 2 feet will split into 1 foot, 1 foot. And then the 1 foot later will split into a half foot, half foot. Gradually, as it keeps going, the waves, there will be more waves, but these waves will be much smaller, will be way much higher frequency. I will show you a video that will demonstrate how these harmonics occur. What happens when we add pure tones, or we add any tones? If you add 2 tones together, they are going to produce complex tones. These tones can be periodic or aperiodic. Let's look at these 2 waves that we have. Here's the top wave. 0 is rest, and from 0 you go up, maximum amplitude is 4, and then rest again. So this is the maximum, this is the compression. And let's see the wavelength from A to E is half, and from E to 15 is half. So actually, no. Second. I. So you get A, B, C, D, E, F, G, H, I. From A to I, this is the length of the complete wave. half of the wave is from A to E. Okay. And the loudness is +4 or 4 decibel. Let's go down to the second wave. It begins here, and C is just about half of this peak here. So one whole wave is going to end here at E. So E go up. E is equals half of that first wave. In other words, one single wave of the second equals a half a wave of the first. Again, from A to I, you have 2 waves in the second, for the second wave, 2 waves. And for the first wave, you have a single wave. So, in other words, the top wave has twice the wavelength, has twice the period, has 50% less the frequency because it's greater. In other words, if you give them each of these waves, if you give them 1 second together, the first wave is going to produce 50% less vibrations than the second wave. The second wave will have twice as many vibrations because you can fit 2 in a single, 2 of these waves are equal to a single wave of the larger one. Another way to think of it is, think of the top wave as the adult male voice, and the lower wave is the adult female voice. The adult female voice is the result of twice as many vibrations for the vocal fold as the adult male's voice. If I say, let's say I have 100 vibrations per second, yours, let's say 200, of course, no. I know mine is 115, 120 years, but I'm trying to give you even numbers so you can kind of relate to them more. So let's say if my voice is 100 times per second, which is the first wave, then yours is 200 times per second. So you can fit 2 waves in the same time as, 1 wave for me. Now you play them exactly at the same time, and you are going to see how they combine. What makes the combination possible is this. If the peak or the maximum amplitude of one wave coincides, is aligned with the maximum amplitude of another wave, then they push in the same direction. They add their energy to each other, and they make a louder part of the tone at that point. So here, the peak of this wave stands at, the amplitude is 3. The amplitude, and you go up of this part of the wave because they come from across from each other and they push in the same direction, that is 2 decibel. So you should be able, it's like, pushing a car. You push, someone else comes and pushes in the same direction, your energies combine, and then you push the car farther, you put more energy. So you add 3 decibels to 2 decibels, and this part, if you go down, is going to increase in loudness to become 5 decibel. Let's take this part. There's 0 here because it's at rest, and then you go up here, 4. So 0 plus 4 is going to give you 4 decibel. And you can keep doing the addition. In the end, you are going to have this pattern. Here's rest, and here's a trough of the wave. And you come to this point here, and then you have a little dip, and then you go up again, and the wave ends here. So now, when we added these 2 waves that they are quite different from each other, we get a very different kind of wave. It is not harmonic anymore. Harmonic means the peak is equal to the trough. and then the wave repeats itself again. So you have a little peak here, and then you go down again, a huge trough. So now, again, because the two waves are very different, you get an aperiodic tone. That, I mean, it has a pattern, but it is not harmonic anymore. A tuning fork is used to tune pianos, to make sure that the frequency of the pianos is the same that they desire it to be. When you hit the tuning fork, it is going to displace it. At the tines of the tuning fork will be displaced, and then they go back and forth, and that will produce compressions and rarefactions in the air that will travel to your ears, and then you will hear the vibrations. You will be able to see if they are high or low frequencies, but each time, just like a pendulum, the tine is gonna be displaced from rest, back to rest, back again farther from rest. So compression, rarefaction, and back and forth. What is interesting about a tuning fork is that no matter how hard or how gently you hit it, it will give you exactly the same number of vibrations per second. It is engineered to be this way. So complex sound waves, when we have two tones that are identical, exactly in wavelength, the same wavelength, the same period, then add them together, play them at the same time, you are going to double the, combine the amount of energy into them, but you will get a single voice, one single voice. So a complex periodic wave consists of two or more frequencies that are systematically related. They are similar, and they have an original frequency, and they also produce harmonics. Harmonics, again, I'm going to explain more. It's a concept that needs a lot of demonstrations. Harmonics, you think of that as I explained the analogy of the string, and it's explained in your textbook. If you let us, you get a guitar string and pluck it, the first time it vibrates, the whole string is going to go down and back, and that will be one piece. If, let's say, the string is 4 feet. The second time the vibration is going to occur, then you have half of the string making one wave, the other half makes an identical wave. But each side is going to make, the wavelength is going to be twice as high as the first vibration. The second vibration will take place, and then that half of the string is going to vibrate the second time. It will split into two vibrations, and instead of 2 feet, it will be 1 foot going up, 1 foot down, and then on the other side you have the same. So you have the whole 4-foot string. Each foot is making its own wave. So you have 4 waves. Each wave is a single foot, and each wave is 4 times the original wave. So that will be 4 harmonics, and each harmonic is 4 times the frequency. Like if the original vibration was 100 times per second, then each one single foot of the string is going to vibrate 4 times as high. So 4 times 100, it's going to give you 400 vibrations per second. If it keeps going, then each time it's going to split. Each piece is going to split, and the whole string will be going into little smaller waves. Again, we'll demonstrate that. I'm going to show you the video. I will post the video on Blackboard. So a harmonic is a pure tone that is propagated through a medium and it produces a systematically related number of vibrations in that medium. The original tone, when the whole string just goes one vibration being displaced the first time, one, and then goes back to rest, one big cycle. That is called the fundamental frequency, or the original frequency in that case. And then all the additional tones that occur afterwards are called harmonics. And actually the video is here. You can click on it and it will show you the harmonics. So I don't have to post it online, and it's really, the guy does a good job demonstrating that. Harmonics are represented on a line spectrum. So a line spectrum is a graph that shows us how harmonics work, and we need to learn how to calculate harmonics. The fundamental frequency always is the lowest frequency in a harmonics series. And because, energy, we put it the first time into the vibration. We can't get in after. We just make the vibration, we set it and let it go, and then it continues after with the energy that we have given it. And as a result, friction and other things are going to decrease that amount of energy. As it decreases, that the vibrations are going to be less and less loud. However, they will be higher and higher frequency, because higher frequency sounds are softer and softer. So in that series, we look at the fundamental frequency as like almost the mother frequency, and all the little frequencies come after as a result of it, and you can calculate them. So every subsequent frequency is a whole multiple integer of the fundamental frequency. I know this sounds like a complex concept, but I'm going to demonstrate and show you how easy it is. So here, we have a line spectrum, and I'd like you to know what a line spectrum is. It is a graph that depicts harmonics in a series. So harmonics, this is a harmonics series. Imagine it like a duck and all the ducklings following it. So let's go back to the analogy of the string and that you see in the video. The string, when you pluck it the first time, let's say it makes, 100 times per second, 100 vibrations per second. So that the period of that vibration, that when you lift the string and let go the first time, it vibrates at that rate, 100 times per second. So that will be the fundamental frequency. And then you go from there, 30, 20, 100, 0. That is the loudness, of that. But again, it is actually increasing in number. Even, if you start negative 30 to negative 20, that is increasing. It doesn't mean that there's no sound. There is, but I'll explain later about the logarithms of the decibel scale. So here's 0. So, excuse me, the second vibration now in that string, when the string splits in half, each half is going to vibrate exactly at double the amount of the number of vibrations like the first one. So simply you get the frequencies lined up. You call the fundamental, you call it number 1, and then the second, call it 2, 3. Number them. Just put numbers. And if you want to figure out the first harmonic here, that is the first harmonic is the first time that the vibration occurs by itself as a repetition. So the fundamental, yes, we call it 1, but it is not the first harmonic. That's the original vibration. So the first harmonic is really line number 2. So you say 2 times 100 is going to give you 200. So when that guitar string splits in, and half of it vibrates in one direction, the other half vibrates in another direction, then that second half is going to make 200 vibrations in 1 second, which is exactly double the number of vibrations of the fundamental frequency. Then it's going to continue to vibrate. The third vibration is going to split the string in 3 pieces. And then that is going to be 300 vibrations. 3 times 100 is 3. So this is what we mean by multiple integers. So you take the number of the vibration in the sequence and say times the fundamental frequency you are given, and then you can just plug in the number there. So 4 times 100 is 400. Nothing is skipped here. All of these little, frequencies occur predictably. There is it's a pattern. And as you go away, as the frequency keeps rising, it will decrease in loudness because the energy dissipates and the energy decreases as you keep going until it reaches a point where it cannot be heard anymore. So again, when calculating the harmonics, you are going to have many questions like this in the exam. You always keep in mind that the fundamental frequency is part of the series. You count it as the first vibration. And then the second one, even though it is the first harmonic, you call it number 2. We just number the columns so we can calculate each one. Because it will be tricky later. There will be another kind of harmonics that we will calculate. So even though the first harmonic is the first copy of the fundamental frequency, for the purpose of the calculations, just call it number 2 or frequency number 2 in that series. So now let's do some exercises. The fundamental frequency of a guitar string is 100 Hertz. What is the first harmonic? So simply, if the fundamental frequency is 100, the first harmonic is the second line. Say 2 times 100 is 200 Hertz. If the fundamental frequency of a vocal fold is 300 Hertz, what is the second harmonic? Now it becomes a little bit dicey because you need to calculate what is the third and what is the fourth. Let's go back here. Let's pretend this is 300. So the first harmonic is going to be 2, that's the second in the series. 2 times 300 this is going to be 600. Okay, the third harmonic will be 3 times 300. Fourth, 4 times 300. 5 times 300. And because of the 300 is a big distance, then these lines are going to be farther and farther apart from each other. So to figure out the 10th, you say 10 times 300 is going to give you 3000. The sixth harmonic of a series equals 875 Hertz. What is the fundamental frequency? Now this is going to force you to reverse your calculations. And you need to just go back and add them 1, 2, 3, 4, 5, and so on. And then you divide 875 by the number of lines to go back. So if you have the sixth harmonic, that means, let's go back here. Sixth harmonic. Be aware of the trick. We said the second line is the first harmonic. So make sure when you find the seventh harmonic, you go from here. 1 harmonic, 2, 3, 4, 5, 6. So in reality, line 7 is your sixth harmonic. So if the sixth harmonic, which under 7 here, you write 875. 875, you divide it by 1, 2, 3, 4, 5, 6, 7, and then you'll be able to figure out the first harmonic. I mean, figure out the fundamental frequency. So an aperiodic sound, you know, when you add aperiodic sounds, they consist of two or more frequencies that are not systematically related. They have no musical tone. They are considered noise. Every kind of noise that we hear is originally made out of many pure tones that are merged and mixed together, and you can't distinguish between one and the other. So there is an equation, there are equipments that can take out these tones and separate them and isolate them, break them down into individual pure tones, but generally, as they are together, all mixed up, like cafeteria noise, for example, or, you know, party noise. Every one of us has pure tones, but you mix all of them together and they become an indiscriminate, you know, mess of sounds that is simply noise. Speech sounds. Speech is a stream of periodic and aperiodic waves mixed together. Vowels are all periodic, all pure tones, like ah, oo, e, o. All of these are pure tones made by the vocal folds. Consonants always have an obstruction in the vocal tract, and many of the consonants are made with no vocal fold vibration whatsoever. Let's take some. S. Try it. Put your thumb and index finger on your larynx, right below your chin here. Say S. Do you feel anything? There's nothing at all. So the sound is made here in the oral cavity, and that is completely aperiodic. There is no pure tone in that sound. Another sound, say F, or F. No vocal fold vibration at all, but you get the sound here. So any sound that is made in the oral cavity is going to have some noise or an aperiodic tones, and any sound that comes out of the vocal folds will have periodic or pure tones. There are two kinds of, let's look at all the sounds. So vowels, all of the vowels are pure tones, all periodic tones. Consonants are two groups. One group is complete noise, complete aperiodic, that is made in the oral cavity and somewhere else. And one group is a combination of vocal fold vibration and oral cavity noise. Let's give you examples of both. Voiceless sounds, as I told you, S, th, f, t, k, p, all of these are voiceless sounds, no vocal fold vibration at all. Let's take some voiced consonants. Voiced, once you say voiced consonant, voicing means vocal fold vibration. So a voiced sound consonant is made as a combination between vocal fold vibration and pure tone and aperiodic tones made in the oral cavity at the same time. Let's take the sound. When you say that is called a voiced consonant. The vocal folds vibrate, and then you have vibrations between your lower lip and your teeth, upper teeth, and then you get that combination of periodic tones and aperiodic. That is a voiced consonant. Let's take the. That is a pure tone and an aperiodic tone. That is a voiced consonant. Let's take Z. You can easily feel the vibration if you put your index finger and your thumb here. Z. Then you are going to get a voiced consonant. Z. So all voiced consonants are a combination of vocal fold vibration of pure tones and aperiodic tones. And you need to be prepared to give examples in the exam of each. We are going to do more in the class. We could go over all of them. So that is it for this section. The next section is going to be available as well shortly. And I hope that you continue to write your questions to, for the exam, to make an exam, and to also test our your colleagues. And we'll discuss some of these questions in the class tomorrow. Thank you.